Make sure you correct me if I say your name. I don't see Amanda. I don't see Chad. I don't see Bridget. There, see, that's why I got to have you correct me. I don't see Austin. He was here but went out. I don't see Sally. Now I see Sally. Cassie went out. And I don't see Jaron. Is Jaron here? Or Jaron, as I like to say. Okay. I keep forgetting to give you your labs, so I brought them here and have them sitting on the desk, so I remembered to give them to you. There's still 7 here, so just make sure you get your lab, or not lab, your test back. Obviously, you've already had a chance to look at it on Moodle, but I don't want to keep them. As another student asked, your lab reports are also on Moodle, so you can look at your lab reports, see what you're being marked wrong on, so you can not make the same mistake more than once. There will be a pre-lab quiz for the lab tomorrow. I will write it this afternoon, just so people aren't like, woo, we don't have one or anything like that. We will have one. Okay, we have a few more things on forces before we turn to energy, and we'll start with the clicker question. What direction must you accelerate to maintain a circular path at constant speed? The options, of course, parallel to the path at all points, toward the center of the circle, away from the center of the circle, or there is no acceleration in constant circular motion. Okay, Sharday, I don't have an answer from you yet. Okay, I think I have an answer from everyone now that's here. So we have 1, 16, 1, and 1. So it was pretty clear, but there were 3 people who didn't remember. If something is going in a circle, the direction of motion is constantly changing. So changing direction means it's accelerating. So this one here couldn't be right because it's changing direction. So then we have to say, what direction does the acceleration have to be if it's going to go in a circle and change direction? Well, if I start going straight forward and then I turn to my left, the acceleration had to be to my left. And if I keep going in a circle, I'll constantly have the acceleration to my left or toward the center of the circle. So the correct answer was toward the center of the circle. And that's actually where we left off on Wednesday. Of course, on Friday, you did some work with it. And you have your last homework problem is basically what you did in class on Friday. Some simple examples here. A car rounding a corner. This is exactly what we did. The car is rounding a corner. The velocity is forward, but it has to have an acceleration toward the center. Now, if that car is accelerating toward the center, Newton's second law says there must be a net force toward the center. And so if you look at the free body diagram on this car, you're going to have something going toward the center. So what force would be pointing toward the center? Friction. It's going to have to be friction. We know gravity would be pointing down. Normal would be pointing normal from the surface, which would be up. Neither of those is pointing toward the center. The only thing that would be left would be friction. And so we'd have friction going toward the center, and then Newton's second law would say the sum of the forces toward the center is equal to the mass times the acceleration toward the center. And we have the abbreviated word centripetal force. Because centripetal force means the force toward the center. And A sub C is centripetal acceleration, the acceleration toward the center. So now I'll do one more step and then answer your question, Diksha. So now applying Newton's second law to this, I would have the force of friction, because that's all the forces going toward the center, is equal to the mass times the acceleration toward the center, which it turns out, you had to have this for Friday, the acceleration toward the center is speed squared over the radius of curvature. What was your question, Disha? Okay. Now, I will point out that the picture, you had this picture here on your Flip Friday, but the situation was the car was both speeding up and going around the corner. What's different if it's speeding up and going around the corner? Okay, its speed is increasing as well as its direction changing. So the speed increasing requires an acceleration in the direction of motion. We call such an acceleration a tangential acceleration. So in the case for your Flip Friday preparation, and I miscounted my forces. I put 2 or 3. It should have been 1 or 2. You could have either on that case said you had a force of friction that was like this, that has 2 components, or you could have said, I'm just going to put 2 separate forces of friction, this one here to accelerate it, and that one there, well, this one here to make it go faster, and the one toward the center to make it go in a circle. Either one I would have accepted. I am sorry that I miscounted. I don't know how I could miscount when you're only going up to 2, but I made that mistake. So something's going in a circle, we have to have this acceleration. Now, just to make sure that there is no confusion about this, I have my favorite demonstrator now, this. Takes me back to when I was a kid, you know, in Liberia, playing around with my slingshot. So if I have this and I swing it around my head, is the bob accelerating at the moment? What direction? Toward the center. Now, a little more technical question. How am I keeping it going in a circle? My hand has to actually be doing a tiny circle so that I'm pulling it forward to keep it going, because the air resistance, the drag force, is going to slow it down. If I don't move my hand, it slows down, so on. Okay, so we always pretend my hand is stationary, but in fact it's doing a little circle to keep it going. Now, if I speed this up, what's happening to the acceleration? Okay, increasing or decreasing? Increasing. And by the equation, we know that the acceleration is equal to v squared, speed squared, divided by the radius. So keeping the same radius and making it go faster means the acceleration is increasing as the speed squared. Now, if I shorten it up, so if I go like this and keep the speed the same, because it has a smaller radius, what does that mean for the acceleration? Smaller radius is also higher acceleration. Now, an unrelated question, but certainly one that was on that pre-test will be again on the post-test and take the exact same thing. If I take this and I swing it around, and let's say that I want to try to hit Toussaint. If I want to hit him, when do I need to let go? Okay, when the velocity is pointing at him is what Tori said. She's the closest, hence the one I heard. So, what position will the bob be when its velocity is pointing towards Toussaint? Okay, so I'm going to try to let go right when it's to my right. I'm going to look this way instead of at Toussaint. So everybody be aware, don't let it hit you. Okay, not very good. Now, I wasn't even looking at him, so, I was only looking at the bob. If I was actually using a slingshot, has anyone here ever actually used a slingshot? No one?
Should we sign waivers?
No, we don't need safety waivers. That's for sissies. We're just going to take our lump. Now, if I was actually using one, if I was like, remember I talked about the ladies who were out there keeping the birds away by hitting the coffee cans. You actually, I'm not going to let go, okay? But I would actually, I'd swing it around my head, and then when I do it, I would actually use a throwing motion as well to get that direction more exact. But, well, it's fun to play with these. That's why Dave Mike and Giants has the song, everybody wants a rock to wrap a string around, right? Because they want to do this. You guys probably know that. No, Nate, you probably don't. You guys don't know good music. You're just too young to know the music of my... Actually, it's not of my generation. It's after mine, but... You know. Okay, so we have that centripetal acceleration, which is the acceleration necessary to go in a circle. Now, just a few more things. Apparently, there was a NASCAR race yesterday. I didn't watch it. I did things like watch the Raiders. No, I didn't watch the Raiders win. I watched the Vikings win. Because the Raider game wasn't on. My wife and son are Viking fans, so they're going to be pretty excited when the Raiders play the Vikings this year. But there was a NASCAR race. And so we had a question about, well, you might have had a question on your reading quiz about race cars taking turns. That's going around a corner. And when they go around that corner, instead of taking it all in one lane like you would if there was a Smoky on your back, they come in and they start up on the outside of the curve and they dive into the inside and then they go out to the outside again. And the question there was, why would they do that? What's the answer? They can take it at a faster speed. Why can they take it at a faster speed? Just requires us to analyze the physics a little. If you look at the radius for the blue arc, it's going to be much longer distance to get to the center of that circular arc than from the red arc. So they're making a larger radius. Since the centripetal acceleration is inversely proportional radius, the centripetal acceleration necessary to stay on that line is smaller than it would have been if they made the tight arc. It also is smaller than it would have been if they would have just stayed on the high line. If you take the high line, you still have a radius that's actually fairly similar to the radius of the red one. I mean, it's longer by the width of the lanes, but it's not that much different, where the blue one, you're able to make it a much larger radius, hence you can go faster. So, unless you're in a situation where the curve is banked right and you have things so you can take the low line at your top speed, that line's going to make it so you can take it faster because it requires less centripetal acceleration. Why is centripetal acceleration an important calculation? Because they have friction giving them their centripetal acceleration if it's a non-banked curve. And so their maximum friction is going to be that coefficient of static friction multiplied by the normal force on a flat surface. That's a fixed value. They can only cut so tight. Now, that brings us to banked curves. Why do we have banked curves on racetracks? Okay, it's so you don't have to rely on friction as much. If you have a banked curve, so when we do banked curves, we tend to do them like this and just show a side view at angle theta. And you have the car on this banked curve, then just like with your homework problem, you draw the forces. You have the force of gravity that always points down. You have the force normal that always points normal to the surface. What direction is this car accelerating if it's going around this curve? Toward the center. So the acceleration is toward the center. So I'm going to put in a different color here so we don't get it confused with the forces, the acceleration. And then because of that acceleration, unlike what you did in the homework, we usually set a coordinate system that has the center direction like this and maybe the y direction here. So I didn't call it x, I just called it the center direction. I still have to have my coordinates perpendicular to each other. But I called it c so I'd remember that's the direction toward the center. And then we apply Newton's second law. Well, if you look at these forces, what do I have to do before I apply Newton's second law? I have to break them into components. If I put these, the central part and the vertical part, to be consistent with your homework just says, well, the force normal, I'm going to break into two pieces. One that's going like that toward the center and one that's going like that up. So I would have force normal center and force normal y. Now, note that you actually had X instead of center, so you change the sign, of course. It'd be minus in the X direction the way your problem has it. And for force of gravity, how much is force of gravity in the center direction? None. And it's downward, so minus in the Y direction. Well, then following along with that homework problem, I do this so I can apply Newton's second law in each direction. I know the acceleration toward the center is v squared over r, because it's going in a circle. And the acceleration in the y direction is 0, because it's not going up or down, it's not accelerating up or down. And thus I can do sum of the forces in the y direction is equal to mass times acceleration in the y direction, which was 0. And so I have force normal y minus force of gravity equals 0. So force normal y is equal to force of gravity, right? And then if I do sum of the forces in the center direction, I have force normal center equals mass times velocity squared over the radius. Wow, that one was done in one step. Now, I think the problem said to put it in terms of force of gravity in G. And you look at these and you say, but there's no force of gravity or G in that. Well, we do know that force of gravity is equal to mg. So that means m must be equal to force of gravity divided by G. So you make that substitution to get it into those variables they gave you. Now I'm going to stop there, but I want to go through some of these steps just to reiterate. On the pre-class part for Flip Friday, you had to go through the setup for this, but we didn't complete the problem in Flip Friday. We did the one for orbiting. Important steps. How did I choose my coordinate system here? Based off the acceleration. And so if it had not been accelerating, for instance, if it had been sitting stationary, then I wouldn't have had the acceleration to choose from. Then I would have fallen to the next one of, well, what coordinate system would have the most vectors resolved? And either this one or a tipped one would have had the same amount resolved. My third one is, well, all things being equal, I'm going to prefer the horizontal vertical because I'm more comfortable with it. But that's a pretty low priority. That's the one just above flip a coin. And once again, force problems, free body diagram, break them into components, apply Newton's second law. You're just going to do that over and over and over with force problems. Yeah?
So your plot would be on that drawing part, would it be is flat? Or where is, I'm confused how that plot cy equals.
Okay, you're talking, let me change color.
On the green one.
I changed to green color because you said on the green one. Okay, so in this figure, what is confusing to you?
Where is C? Like what is C slanted?
C, okay, this thing that I put a box around is my direction definitions. Okay. So the C direction was toward the center of the circle, which was left in this picture.
So we're not turning it.
Right, I'm not tipping in this case because the acceleration was toward the center. Yes, Dixon.
Next to your force normal, is that a K with the arrow going up? Or is that
K.
Just,
No, that's an arrowhead for the component.
Oh.
All right, I believe I have another clicker question here then. Nope, not yet. I have this about the centrifuge. The reason I have the centrifuge repeated is because people often get confused between a fictitious force and what's going on here. So what's a fictitious force? The first example of a fictitious force is centrifugal force. And a lot of people grew up having heard about centrifugal force. But it's not a real force. It is a perceived force. If you're in the car going around the corner, you feel like you are being pushed into the door of the car. But the fact is that inertia is trying to keep you in a straight line. You have to have a force to change your direction. And so that door is pushing you to change your direction. you're not pushing outward into the door is pushing inward on you. Now, of course, Newton's third law says the force of the door pushing in on you is equal and opposite to your force pushing on it. But that force is there because inertia is trying to keep you straight, and a force is necessary to change the direction. And that's the same thing that goes on with the centrifuge. You take those little test tubes and you put your junk in it, whatever it happens to be, and you spin it really fast, and everything has a propensity to go in a straight line. Now, what types of things have more propensity to go in a straight line? More massive or less massive? More massive. Because mass is what we measure inertia with. So things with more mass have more inertia. They're wanting to go straight more. Now, how that breaks down in centrifuge is the mass per unit volume, the density. Things that are more dense have a greater inertia. They try to go straight, and so they get pushed to the outside. Things that are less dense, they're easier to change their direction, and they get pushed inside because they have less inertia. So a centrifuge, you have that word centrifuge, which everybody's going to say, well, centrifugal. You must be validating centrifugal force. No, it's not actually validating centrifugal force. It's using inertia. Something goes in a circle, inertia tries to make it go straight, and it causes things to separate by density. Now, clicker question number 2. Why does the centrifuge move more dense materials to the outer portion of the spinning tube? Waiting on you, Jerry. There we go. Okay, this time we have 17 people who said inertia, 2 that said centrifugal, and 2 that said centripetal. Now, the 17 people are right. Let me just randomly pick on somebody. I'm going to pick on James, back row. Why is centrifugal, why is that incorrect?
Because the inertia is wanting to push it outward.
Now that's a correct answer on why inertia is correct, but there's an easy answer why centrifugal is incorrect. Yeah, because it doesn't exist. Since it doesn't exist, that couldn't be the right answer. Centripetal is a more complicated one. Why is that not the answer? That's not the answer because the centripetal force, of course, you have the beaker is pushing in and pushing stuff in circles, but it's only doing that because inertia is trying to keep things straight. And so that's why we say that it's the inertia rather than a force that's doing it. Yes?
So we learned on Friday that centripetal is also a fictitious force.
Well, centripetal is a summation. It's not an actual force. Right? It means some force is what it says.
Force.
Yeah.
In this scenario, I have a hard time grasping what is the actual force causing uniform circulation.
It depends on where you are. If you're touching the edge, then it's going to be the normal force from the beaker onto the particle. If you're not touching the edge, it's going to be the force between particles that are in your fluid. Right, because centripetal force, it can't just be centripetal because it's not an actual force. It's what you get from adding things out.
Right. Yes. So we must be able to.
Alrighty. And we've already done everything I'm going to do pretty much with orbits because you did that in Flip Friday. We have Kepler's laws that say that planets do elliptical orbits with the sun at one of the 2 focal points, and that in the orbit, when the planet is closer to the sun, it goes faster. When it's farther from the sun, it goes slower. And the equation that you worked out, that the period of orbit squared is proportional to the distance, the radius of the orbit cubed. Those are Kepler's 3 laws that Kepler came up with just from observing data. It was from no physics theory whatsoever. 100 years later, Newton was able to explain using physics why those were correct. And so what you did was you did the Newton's calculation for one of the 3 laws. And we assume circular orbits for our calculation because it's simpler. But the work still comes out the same. So that's all we're going to have for Kepler's laws, nothing else. The Coriolis effect is the result of another fictitious force, the Coriolis force. Now, the Coriolis force is the phenomenon that if you were on a merry-go-round, and let's imagine that Tori and I are on a merry-go-round. We're going around in circles. And I have a ball and I want to throw the ball to Tori. Thinking very logically, if we're stationary and I want to throw the ball to Tori, which I have to do it because no one else could visualize me throwing the ball to Tori if I don't actually do it. So if I want to throw the ball to Tori, where do I aim in the horizontal direction? Let's not worry about the vertical right now, just in the horizontal. Straight toward her. All right, no problem. Now, what if we were going in circles around each other? She wants to throw it back to me. Where does she have to aim? In front, she has to lead. So I'm going like this, and you throw it out here so that I get to it when the ball gets to me. So now, if we're sitting on a merry-go-round going in circles, and we're going slow enough that we're not too busy, I look over there, and she appears stationary to me. I see her at the same angle all the time, even though we're going in circles. So if I don't think, I might start to think she's just stationary and throw the ball straight at her. But if I throw the ball straight at her when she's going in a circle, what's going to happen? It's going to fly behind her because she was going in a circle. Now, as I watch the ball move, what's it going to look like, the path it took to me? It's going to look like it curved away from her. I'll be like, what kind of, hocus pocus juju is this? And I would have to learn that I'm going to have to throw it out here in front of her so that she comes around and catches it and curves into her. Well, that effect is what we call the Coriolis effect. It's an effect caused by a rotating reference frame. If I'm in a rotating reference frame and I perceive myself as stationary, then I'm going to see things a little different. And so the Coriolis effect is something that occurs because of being in a rotating reference frame. And so how does it affect us on Earth? Imagine that you are at the equator and you throw a ball north. You throw it straight north. The Earth is curving. So the ball was moving. What direction is the Earth rotating? Toward the sun rises in the east because we're rotating toward the east. So at the equator, you're rotating toward the east. I throw it straight north. It's going to have a component of its velocity that's east because of my rotation, and a northerly component because I threw it north. Well, as it goes up on the Earth, its radius for the center of rotation gets smaller. If you're on something that's a rigid object that's rotating, what happens to the speed as you get closer to the center? It decreases. So that means the speed at which the Earth is moving east slows down as you move north. But the ball is just in the air. It's going to maintain its constant easterly velocity. And so it's going to be going faster to the east than the ground is. And so if you were to plot the path that it takes when I throw it north from the equator, you would see it start up here and then start heading to the east. It's not heading to the east because of some magic or voodoo. It's because it's going at a constant speed to the east, but as it goes north, the Earth is not going as fast to the east because you're smaller radius from the axis of rotation. And so it makes it look like it curved with respect to the Earth. It didn't really do that curve. It was that we have a moving, rotating reference frame that's also, well, it's accelerating. And so that's what the Coriolis effect is. Now, what's the most common place that you see the Coriolis effect? And I'll say no as soon as you answer correctly. Okay, well, that one's true. In hurricanes, it's true. Most people say, well, when I look at the toilet and see the direction the water drains. And it is true that the Coriolis effect would make toilets drain the way we see them drain. Maybe 0.01% of the time more than it goes the other direction. It's a pretty small effect when you're talking the size of a toilet. And so our toilets are actually made so the water is already directed in the way that it's slightly more likely to go, so that they will drain more efficiently. So you can't really use the toilet as the example. And anyone who's been scientifically minded has filled up the kitchen sink, pulled the plug and watched the drain, and has noticed, hey, sometimes it spins one way and sometimes it spins the other. And like I said, if you were to do it many, many times, you find a slightly bigger percentage that goes the, as you look down counterclockwise direction. But it's not very many because there are other little things, just the random motions of the water when you pull the plug that might make it spin the other direction. But in hurricanes, they do occur because of this Coriolis effect. So you have, if you look here, this is showing weather patterns on Earth. It tends to be hot at the equator. Because it's hot at the equator, air expands, gets hot, molecules go faster. That's what it means to have a higher temperature. Because the molecules are going faster, they bounce off each other harder and push each other apart, so you get a lower density. Lower density materials float on higher density materials, so that hot air floats up. And so you have here the hot air. Let me change the color. I know I didn't get that fully erased. I'll get it. You have the hot air that floats up at the equator. Well, when it floats up, the air pressure decreases, it expands, and when things expand, they cool. And so that hot air cools as it goes up. Cool air can't hold as much water, and so that hot air drops its moisture, hence you have a lot of rain in the tropical regions because the hot air drops its moisture as it goes up and cools. And then that cool air has to go either north or south, right? Pretty obvious it can't go anywhere else. And so that cool air goes either north or south, and because it's cool, it's more dense and it starts falling back down. And so that air comes down to the earth around 30 degrees north and south latitude. So now you have this dry air that's falling. As it falls, it gets compressed. As it gets compressed, it gets hotter. So you have hot, dry air that's coming down. Of course, hot, dry air doesn't have moisture in it, right? That's kind of the definition. And so you tend to have your deserts there in that region about 30 degrees north and south because that's where the hot, dry air is falling. And then that hot, dry air will cycle back toward the equator. That's basically what drives our weather patterns. And so as that air moves, you end up getting these kinds of things that happen because of the Coriolis effect, making your tornadoes or cyclones or hurricanes, where you are, what type of, your tropical storms would be a general term, your typhoons, if you're other places. But they're caused by that Coriolis effect and the natural motions of what we have in physics.
I feel like I'm not quite grasping that. Like with the ball example, I think what we were theorizing is that when you release the ball, it's no longer like tied to the system that you're spinning.
Right.
So that its velocity changes as you're.
Well, its velocity isn't changing, but the Earth's velocity is changing.
Yeah, its velocity is constant. The radius is changing. So,
yeah.
But with the hurricane, it's still like attached to the Earth.
Well, if you look here, if you have air that's going toward the equator, it bends one way. If you have air that's going away from the equator, it bends the other direction. And so that's what causes you to have the cyclonic storms.
That makes sense.
Okay, I think we're ready to get into energy. Nope, got to have the question on this first. Why do we observe the Coriolis effect if the Coriolis force is fictitious? It doesn't exist. I finally have all of the clicker IDs incorrectly now. So proud of myself. Okay, so we had 1, 19, and 1. And that's right. It's because the Earth is rotating. Now, one last thing before I leave this and go to energy. The fictitious forces we've learned then are centrifugal force and the Coriolis force. if you treat a rotating reference frame as a valid reference frame, which you can, it doesn't fit what we call an inertial reference frame. Inertial reference frames are reference frames where Newton's laws apply. Most specifically, where Newton's first law applies, that says an object has constant motion unless acted on by force. If you're in a rotating reference frame, an object is going to have a constant force pushing in to stay in a stationary circle. And so if you consider your rotating reference frame, then you say, okay, this is a non-inertial reference frame. Newton's first law doesn't apply in this reference frame. And if Newton's first law doesn't apply, then I can treat the centrifugal force as real. But since we do all of our physics in inertial reference frames where Newton's laws apply, it's a fictitious force. All right, energy. At least my recollection says energy. This is a pretty picture from our textbook, and the question is, what forms of energy do you see? Now, we haven't even defined what energy is yet, but when you look at this just based on your, maybe it's very well studied or maybe very nebulous understanding of energy, what do you see as forms of energy here? I will be described. Okay, you said wind?
Yeah.
All the particles observed. Can you narrow that down a little for me?
Not really.
Okay. Chemical energy. Solar.
Thermal.
Okay. I think that's what Ryan was getting at.
Well, it equals MC squared. Every particle of the matter.
Oh, okay. That's what you meant.
Every piece of matter in existence is energy.
Okay. So that's called the rest energy.
Can we do kinetic energy?
Well, I'll go ahead and put it. There's a subtlety that doesn't need to be discussed now. Okay. Gravitational. There's lots of different types of energy here. I'm sure there's more if we were to analyze more, but you can see lots of types of energy. Now, there's some important things we need to understand about energy, like what in the world is it? Right? Some people, I'm sure, know very well what energy is. Others, not so much. The textbook says there's no perfect definition for energy, which probably leaves you cheering like, hooray, I'm sure I'm going to understand this if there's no perfect definition for it. But the simplest working definition for energy is the ability to do work. Now, you all should recognize that's just pushing it off because I don't know what work is. So I'm defining energy as the ability to do work and don't know what work is. So we're going to start by looking at what work is and then work our way through to understand how energy is. Or how energy works. So what is work? Work is, at its simplest, a transfer of energy. Work is a force that makes something move. So now if you look at a person sitting in a chair, if you're just sitting stationary in that chair is putting a force in you, a normal force, right? You're putting a force in the chair downward. You have gravity putting a force down on you. But if you're not moving, there's no work done. And in fact, if you're not moving parallel to the force, there's no work done. So the mathematical definition of work is force dotted with the distance. And some of you may have taken, like algebra and learned what a dot product is. Well, it has to be a vector algebra class, something where you dealt with vectors. A dot product means that you multiply the parallel parts. So that means the force vector multiplied by the component of distance parallel to the force vector. A dot product is also called, and I'll change colors for this so we see it standing out, a scalar product. because it's a way of multiplying two vectors to get a scalar answer. So work is a scalar. It has no direction to it. Force was a vector. The displacement is a vector, but the work is a scalar. Now, before I do any calculation, let's just look at the units. What are the units of force? Okay, so we have units of force, which are newtons. And then what are the units of distance? Meters. And so that gives me units of Newton meters. So the unit of work is a Newton meter. And because this is so common in physics, we give it its own name, the joule. A J is equal to a joule. And yeah, that's an odd spelling of joule. In graduate school, I had a professor who thought he was immensely humorous that said we should call it a jowl because, OU can have all kinds of different sounds. But it's a joule. It's a dude's, well, I think it's his title rather than his family name, but it's still a name. So we have units of joules, or newtons times meters. Remember, a newton is a kilogram meter per second squared. So if you multiply newton times a meter, that's also a kilogram meter squared per second squared. So these are all the same units, the units for energy. Now there was one reading quiz question about the calorie. The calorie was originally a unit for heat. There was the caloric theory about how heat worked. They said it was a fluid, blah, 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 blah. And then William Prescott Joule, I guess it is his family name, did an experiment that showed that heat was just a form of energy. And so then we had the joule equivalent of heat that said that 1 joule is equal to 4.186 calories. Now our textbook used 4.184. That's not the standard value. You will find different values if you look in reference books. But that's our standard for 1 joule is 4.186 calories. A dietary calorie is 1,000 calories, hence the dietary calorie, or our textbook called it the food calorie, is 4,186 joules of energy. Okay, now, how to do the calculation. Imagine that I have a force vector that's pointing like that, and I have a distance that's pointing like this, and there's an angle of theta between the two. If I'm going to find the parallel parts, I'm going to have to break one of these two into components. So, staying with the back row, Edward, which one would you prefer to break into components? The force or the distance? Okay, so he's going to break the force. By him choosing the force, that means we're going to choose our coordinate system like this. We put our force on there and we say how much is in this direction, because that's going to be the parallel component. So if I have my force magnitude on that side, those parallel, remember absolute value, means magnitude. So if I have that magnitude, how much is going to be in the adjacent side here? How much? Okay, this side here is going to be F cosine of theta. So if I want to calculate the work and I have to multiply just the parallel parts, I'm going to have force cosine of theta was the amount of the force parallel to the distance d. And so I have force times distance times cosine theta, where theta is the angle between the force and the distance. Hence this form here. This way that's in the red box is the more succinct way of writing the work definition. Of course, the most correct is integral of force vector dot dx, but that only makes sense tomorrow in calculus class. But the dot product is more succinct. It has more meaning to it. But when you get to doing the calculation, you're going to use this one here most of the time. Now, a clicker question. Which figures, so this is, I'm sorry the K got cut off. This is going to be answer all that are correct and then hit answer. which figures illustrate work being done on the briefcase or the lawnmower? I forgot the top was a lawnmower, so the briefcase or the lawnmower. And you can see the equation is up there at the top of the screen. Okay, I'm still missing Cassie, Sally, and Toussaint. Now just Cassie and Toussaint. And now just Toussaint. I got you now. You got a problem there, Toussaint? Okay. Well, you already have a majority of them in, so you're not going to lose credit for not answering this one, so I'm going to go on. Okay, so the answers we had were 3 who said A, 0 who said B, 5 who said C, 17 who said D, and 14 who said E. Now I'm going to have people look at each one of these, and I'm going to ask 2 questions and have people answer. So number 1, actually, 1 question. Does it move parallel to the force? So in the first picture, the force here, now we're talking about the lawnmower. The force is down and forward. Does it move parallel to that? Ann says yes. How can Ann be right? Because she is. Because it has a component that's parallel, right? The force is going like this. The distance is like that. There's a component that's parallel. And so that meant A was a correct answer because it moved parallel to the force. Diksha.
Okay, so when you say force, which one
I'm talking about the force that it shows, the force of the man pushing on it.
just that one?
Yeah, just the one that's shown.
So then how is there a parallel to...
Because this force has a component shown here that's force cosine theta, that's parallel to the distance it moves. Not all of the force was parallel, but some of it was, so there is work done. Okay, going next to Bridget. For picture B, does it move parallel to the force? No, because distance is 0. Hence, it couldn't be that one, and everybody got that one right. No motion means no work. Okay, Cassie, C, does it move parallel to the force? No. She says no, why not? They're perpendicular. If they're perpendicular, there's no components parallel. That's the definition of perpendicular. And so that one there was wrong. Diksha, D, does it move parallel to the force? Yes, it does, because the force was vertical. The motion was at an angle that included vertical as part of it. And so that was correct. And then finally, Michaela, for picture E, does it move parallel to the force? Okay, yes is the right answer. An even better answer would be it's anti-parallel, because the force is up and the distance is down. Yes is still the correct answer. So it has work, but in this case, because the force is the opposite direction to the distance, it's a negative work. Question?
Question, it's not really important, but in real life, is Z possible? Like, wouldn't you have to be pulling it with you?
Okay, in real life, if you could walk at a constant speed, once you get started and before you slow down, it's possible. But the fact is you can't really walk at a constant speed. So to make it more realistic, you'd have to do something like put it on the back of a trailer and drive at a constant speed with the trailer. Then it gets more realistic. Because, yeah, our walking is very herky-jerky. Okay, we're out of time, so I will stop here. Let me point out problem number 1 on the homework. It was for no credit on the homework because it includes the ideas that I would have gotten to on the next 2 slides. I only saw part A when I assigned it, and part A was perfectly appropriate. But parts B and C required this information.
Which question?
I think it's the one with the loop, the roller coaster.
Question on this real quick.
Seriously. Just trying to stop the recording. Still trying to stop the recording. See, I'm tapping that button.
Yep, I have the same problem with my phone sometimes.
It's a stable operating system. Okay, what's your question eventually?
So this is the equation that I have, if I'm moving this correct. And so when we're talking about the moon getting closer to Earth, if you plug it in, I feel like the time would increase, right? If you plug in a shorter radius.
Okay, if R gets shorter, then this whole thing got shorter, right?
Yeah, so the time would be faster. No,
I know.
The time would be a smaller time. Now, does it ask about the time or does it ask about the speed?
Oh, speed.
Okay, so for the speed,
So it's
we
a
come
smaller
up.
time.
For the speed, we'll come up to this one. I think it's this one. Where's your answer on this one?
This box.
Okay, so V is equal to GM over R. So this was.
The moon is getting closer to Earth.
Where did I write that?
Okay.
Yeah, there it is. Closer to Earth. Okay. So if R is getting smaller, then what's happening to V?
It's increasing. Okay.
Come on, it's. Wonder what happens if I close all of them. Well, that one didn't work either.
For one, all of one's no credit, or part A on one is credit, and the rest is
All I have the option of
Okay.
is all of.
Okay, awesome. Thank you.
Yes.
Right now.
Oh. I'll bet you I can do it with the style.